Good morning students. Welcome to 13th video on system of particles and rotational motion. In this video we are going to know what is expression for moment of inertia of a rigid rod with a pair of mass attached to its ends. Later radius of gyration, kinematics of rotational motion equations. Then we discussed the concept of the angular momentum of the particles rotating about an axis. Let us know what is the expression for moment of inertia of a rigid rod. So consider a rigid rod of length L with a negligible mass with a pair of mass attached to its ends rotating about an axis passing through the geometric center of the rod, which is center of mass of this rod. So now we want to know moment of inertia of this rigid rod with a pair of mass attached to its ends, which is given by, moment of inertia is product of mass into the square of the distance from the axis of rotation. Therefore, I is equal to mass at this end, that is m by 2 into square of the distance L by 2 square plus mass attached to at other end of the rod, it is again m by 2 plus the distance from the axis of rotation, that is L by 2 square. So on simplifying, we get I is equal to m L square divided by 4. So I is equal to m L square by 4 is the expression for moment of inertia of a rigid rod with a pair of mass attached to its ends. So now let us discuss radius of gyration. Radius of gyration. So radius of gyration is denoted by K. To know what is radius of gyration, let us consider a rigid body which is capable of rotating about an axis, say z axis. We choose a point in the rigid body where the entire mass is assumed to be concentrated, and let us say that point is C, where that point C is called center of mass of this rigid body. Suppose if this point where the entire mass is assumed to be concentrated, which is at a distance k from the axis of rotation, then radius of gyration is the distance from the axis of rotation to the point where entire mass is assumed to be concentrated. Radius of gyration is defined as the distance from the axis of rotation to a point where entire mass is assumed to be concentrated. If k is the distance from the axis of rotation to the point where the entire mass is assumed to be concentrated of a rigid body which is capable of rotating about an axis, then its moment of inertia can be written as I is equal to mk square. Moment of inertia is product of mass into square of the distance from the axis of rotation. If k is the distance from the axis of rotation, m is the mass of the rigid body, then I is equal to mk square. So therefore, the radius of gyration is given by k is equal to root of I divided by m. Suppose if I want to know what is radius of gyration of a rigid rod capable of rotating about an axis, then I can estimate for rigid rod. the radius of gyration is k is equal to, it is root of I means m L square divided by 4, L square divided by 4m, because it is I by m, so m will get cancelled. Root of L square divided by 4 is simply L by m. Thus, if you know moment of inertia, you can estimate the radius of gyration, or in other words, if you know radius of gyration, I can estimate moment of inertia. So this is about the radius of gyration. So let us know the kinematics of equation or rotational motion. Kinematics of rotational, which means equations for rotational motion. Kinematics of rotational motion means we want to write the equations for rotational motion. So we have seen three basic equations in mechanics for linear motion, for constant acceleration. Similarly, we can write those three equations in their rotational analog, assuming that angular acceleration value is constant. The first equation is omega is equal to omega naught plus alpha t, where omega is final angular velocity, omega naught is initial angular velocity, alpha is angular acceleration, whose t is time. Second equation is theta is equal to omega naught t plus half alpha t square. This is second equation of rotational motion with theta displacement, angular displacement, initial angular velocity, then angular acceleration alpha. And third is omega square is equal to omega naught square plus 2 alpha theta, where omega is final angular velocity, omega naught is initial angular velocity, alpha is angular acceleration, theta is angular displacement. Remember, we are using these three equations and keeping in mind that angular acceleration remains constant. So now let us know angular momentum in case of particle rotating about a fixed axis. Angular momentum of particles rotating about fixed axis, because we know a rigid body is rotating about a fixed axis, so therefore we want to know angular momentum of particles rotating about fixed axis. We know that angular momentum of system of particles is given by vector L is equal to summation of I is equal to 1 to N of vector Ri cross vector Pi. This is the expression for angular momentum of system of particles. Vector L is equal to summation of I is equal to 1 to N of Ri cross Pi, where Ri is position vector of the ith particle, Pi is momentum, linear momentum of ith particle. Suppose if the system of particles rotates about a fixed axis, say z axis, is if the particles rotates about z axis, say a fixed axis, say z axis, then this equation can be written as vector L is equal to summation of I is equal to 1 to n of magnitude of position vector, say Ri, into magnitude of linear momentum vector Pi into k cap. Is cross product of two vector which is Ri Pi sin theta into k cap. So we have taken maximum, that is when R and P are perpendicular to each other, so then sin 90 is 1. So in that case Ri Pi and cross product of these two is always perpendicular to both this vector. If Ri is along x axis, Pi is along y axis, then the cross product of those two, that is angular momentum, is along z axis, so it is written as k cap. So I will call this as equation 1. So since Pi stands for linear momentum of I particle, Pi is mi into Vi. Pi is mi into Vi, then and also Vi is Ri into omega. Vi is Ri into omega, then equation 1 becomes vector L is equal to summation of I is equal to 1 to n of Ri here. Instead of Pi I can write mi Vi, instead of Vi I can write Ri into omega. So therefore it is mi Ri square, because Ri into Ri is Ri square, mi Ri square into omega into k cap. So we call this as equation 2. Since summation of I is equal to 1 to n of mi Ri square, product of mass into square of the perpendicular distance, which is nothing but moment of inertia I. Therefore angular momentum vector L is equal to, instead of this I can write I omega into k cap. So its magnitude is a modulus of L is equal to L, which is equal to I omega. We call this as equation 3. So we obtained a very important conclusion that angular momentum of the system of particles or angular momentum of a rigid body rotating about an axis is just the product of moment of inertia into angular velocity. We know linear momentum V is equal to m into V. So m is replaced by I in case of rotational motion, V is replaced by omega. Thus angular momentum of a rigid body is the product of moment of inertia into angular velocity.